Welcome to lecture number 3 for ECE 111. This week we're looking at using MATLAB to solve problems that you run into in trigonometry, Math 105. Now, Math 105 appears right here in the ECE curriculum. It's the prereq for calculus, prereq for circuits. The reason for that is we start dealing with sine waves in circuits 1, second half. When you're dealing with DC signals, like signals from a battery, you can use real numbers. When you start dealing with sine waves, you need to start dealing with sine and cosine, two numbers. And to do that, we use a thing called complex numbers. With complex numbers, it's kind of like polar form. I can represent a point with two coordinates, the x and y coordinate, north and south, east, west, or distance and angle. The objective here is to relate sine and cosine to unit circles, convert from rectangular to polar coordinates, calculate the position of a robotic arm, given the joint angles, calculate the angles of the robotic arm, given the tip position, and use the MATLAB function fminsearch. So starting out, if you go to Wikipedia, trigonometry is defined as the study of triangles. This dates all the way back to the 3rd century BC. That might seem like kind of an archaic topic, but actually trigonometry is fundamental for electrical computer engineering, hence the reason it's a prereq for pretty much everything. For example, if you look at the power outlet, the power in the US is at 60 hertz. That's a sine wave. That comes from trigonometry. If you have a subwoofer passes frequencies below 250 hertz. That operates on sine waves. New motors that are coming out, like quadcopters, electric motors, electric cars, those are all ECE motors. Those are driven by sine waves. And if you want to analyze the system that's described by differential equations, which pretty much means everything, that depends upon being able to use complex numbers, which have the origin in sines and cosines and trigonometry. Likewise, trigonometry might seem like an archaic topic, but actually it's much more than that. So let's start out with sine, cosine, and tangent. Wikipedia has trigonometry as the study of triangles. Actually, I would say it's the study of circles. If you take a circle, pick a point on the circle and spin it around, the x-axis maps out a cosine. If I start right here at plus 1, it goes from 1 to 0 to minus 1 to 0 to plus 1. So cosine is the x-axis for a point on a unit circle. The y-axis is sine. Take this point, the y-axis is 0, 1, 0, minus 1, 0. That maps out a sine wave. And there's also the trig function tangent. Tangent is take a point tangent to the circle at this point plus 1. The height of that line is the tangent. So at 0 degrees, the tangent is 0. At 45 degrees, tangent's 1. At 90 degrees, tangent goes to infinity. So trigonometry all relates to the unit circle. If you want to plot sine versus cosine, you can do that in MATLAB. There's a thing called frequency, omega. That's how fast a sine wave is spinning. Let's start with omega equals 1. If I have t goes from 0 to 10, frequency is 1. Plot cosine omega t, sine omega t. This is what it looks like. Cosine starts at 1, goes to minus 1 plus 1. Again on the unit circle. If I have a circle, take this point and spin it, the x-axis is cosine. The y-axis is sine. It goes from 0 to 1 to 0 to minus 1, 0 to 1, 0 to minus 1. That's the y-axis. In addition, note that the period is 2 pi. In English, we use hertz, cycles per second. Hertz are not the natural unit. The natural unit are radians per second. And the cosine is periodic in 2 pi. So that's going all the way around the circle is 2 pi. That's kind of a rule of thumb that anytime you deal with English units, the units are wrong. The math works out much better if you use natural units like radians. So again, the MATLAB functions sine and cosine are periodic in 2 pi, not 360. MATLAB uses radians. Also note that you can convert 360 degrees is one cycle, 2 pi is one cycle. So if I want to convert from degrees to radians, so to degrees, if I multiply times 2 pi and divide by 360, that'll give you radians. And I can also convert from hertz to radians per second. 1 hertz is 1 cycle per second. That's equal to, all the way around the circle, 2 pi radians per second. So to convert to the natural frequency, that's 2 pi times hertz. Again, pretty much anything English is wrong. If I want to plot a 1 hertz sine wave, what I need to do is make the frequency 2 pi. So again, do the same thing we did before. Plot time from 0 to 10 seconds. Now the frequency is 2 pi radians per second. Plot cosine omega t, sine omega t versus time. I get this. And notice the cosine term is a peak at 1, at 0, 1, 2, 3, 4, 5. This is 1 cycle per second, 1 hertz, or 2 pi radians per second. Now with sine waves, there's two ways to represent a sine wave. I can represent it as sine and cosine. I can also represent it as an amplitude and an angle. That's called rectangular form and polar form. And they're both equivalent. I can convert from one to the other. The conversion, kind of see over here, if this is the cosine, here's the sine axis. The amplitude is the square root of a squared plus b squared. The angle is arctangent b over a. For example, suppose I have the sine wave 5 cosine 6t minus 1. Here, this is in polar form. Polar form is actually much easier to see when it comes to graphs. There is an equivalent rectangular form, but it's kind of hard to see what's going on. In polar form, the amplitude, well, I can plot it this way. T goes from 0 to 2. Here's y, 5 cosine of 6t minus 1, plot. That's what it looks like. Where the numbers come from, this number 5 is the amplitude. The peak is this term. The peak is 5. The frequency is 6. Here's the period, 0 crossing to 0 crossing. The period is 1.047 seconds. The frequency is 1 over period. So omega is 1 over 1.0475. 475 hertz times 2 pi to get to radians per second. That gives you 6. And the constant is the delay. A cosine is a peak at t equals 0. This is delayed by 1 radian. And I can see that on the graph. This is 1 cycle, 360 degrees. 1 cycle is 1.047 seconds. The delay is about 0.166 seconds. So the phase shift, the delay is 1 radian. The period is 1/6 of a second, or 6 radians per second. So it's going to be a delay of 1/6 of a second. Or going backwards, this delay is 1/6 of a second, 0.166 seconds. The period is 1.047 seconds. And 1 cycle is 2 pi radians. That gives you 1. So that's kind of one thing to note. There's two forms. There's rectangular form and polar form. In the lab, when you'll use an oscilloscope or look at a graph, polar form is much more natural. So personally what I do is if I'm in the lab, I use polar form. That gives me the amplitude and the delay. In calculations, I like rectangular form, sines and cosines. But they're interchangeable. So looking at sines and cosines versus circles. It shouldn't be surprising that if I let x be cosine, y be sine, plot x versus y, I get a circle. That's kind of the definition of sine and cosine. It also shouldn't be surprising that you have the trig identity sine squared plus cosine squared equals 1. Basically that says if I have a circle with a radius of 1, the radius is 1, which is kind of like a no-brainer. That also leads to polar coordinates. Now, if I have an xy plane and I want to specify a point P, like let's call this point right here, P. I could specify that by its x and y coordinates. That's in Cartesian coordinates. I can also specify that point by the amplitude and the angle. That's polar coordinates. And the two are related. If I take the real or x squared plus y squared, that's equal to r squared. If I take the arctangent of y over x, that's the angle. And I can convert the other way around. The x-coordinate is r times the cosine of theta. The y-coordinate is r times sine theta. In terms of the angle is the arctangent of y over x. There's actually two arctangent functions in MATLAB. There's arctan and arctan2. Arctangent is you give it a single number, y over x. The problem with arctangent is it only gives answers between minus 90 and plus 90 degrees. So if you look at the quadrants, so I have y over x, here's y, x. If the answer is positive, I don't know am I in this quadrant or this quadrant. Or if the answer is negative, I could be one of these two quadrants. What arctan2 does is you give it y and x separately. That way it knows which quadrant you're in, and then can give you the correct angle between minus 180 degrees and plus 180. So we're going to be using arctan2. So some things you can do with polar coordinates. With polar coordinates, you can create some pretty plots. The trick in MATLAB is when you do the plot command in MATLAB, plot always plots in Cartesian coordinates, x versus y. If I want to plot a function in polar coordinates, I've got to convert from polar to rectangular, then plot. So let's start out with r equals sine theta or r equals cosine theta. In MATLAB, I could plot those. For example, if I say for cosine theta, let angle go between 0 and 2 pi. So this goes between 0 and 1, steps at 0.005. So this is 201 points. Times 2 pi, so this goes from 0 to 2 pi with 201 points. Let r be cosine theta. To plot that, I need to convert to rectangular coordinates. X is r cosine theta, y is r sine theta. I need to use that dot notation. That tells MATLAB, don't treat these like matrices. Treat this as 201 different numbers. Analyze each one separately. Plot x versus y. And what you get is a circle. R equals cosine theta is the blue circle. R equals sine theta is the red circle. So again, sine and cosine are all related to circles. I can do a little bit more fancy graphs. I could do a four-leaf clover. If I let r equals cosine 2 theta. Here, angle goes between 0 and 2 pi. R is cosine 2 theta. Plot it. To plot, I need to convert to rectangular coordinates. X is r cosine theta, y is r sine theta. Plot. I get a clover. And if you want to show off, MATLAB actually has pretty good animation. I can plot the unit circle, that's in green. I can plot r equals cosine 2 theta in blue, and then this red line, that's like a radar sweeping around. That's showing the distance at that angle is cosine 2 theta. And to do that, I'm going to create a couple different functions. In my plot command, I'll plot x0 versus y0 in green. x0 and y0 are just the unit circle. That's the green line. I'll plot x versus y in blue. X versus y is the clover. I'll then plot the point x, y as a red circle. That's this red circle moving around. And then draw a line from the origin to your point as a red line. And that's what that looks like. So this is like I had a radar dish at the airport sweeping around. If the target is moving as r equals cosine 2 theta, the red line's the target, that maps out a clover. Kind of fun things you can do in MATLAB. A linear spiral. If it let r be angle over 30, that gives you a linear spiral. And to see that, there it is. If the radius is angle over 30, as I spin around, the radius r gets bigger and bigger. That gives you a spiral where the spacing between arms is constant. And I can also do a Lissajous figure. This is what a Lissajous figure looks like. If I plot sine versus cosine, there it is. Make it 3 to 1. That's a Lissajous figure. If you ever watch like the Mad Frank creature feature Friday night movie, a little bit longer, they oftentimes have Lissajous figures. The way you generate that is on an oscilloscope. I apply a sine wave to the x-axis, sine wave to the y-axis, and make the y-axis 3 times the frequency of the x-axis. If I do that at exactly 3 times, the figure's stationary. If the frequency is slightly off, that's what this DQ does, it looks like a rotating crown. And so it's kind of easy to generate, kind of pretty common in science fiction movies. And the ratio between these two tells you which type of Lissajous figure you have. So this is a 3 to 1 ratio. If I get bored, I can go into MATLAB and stop this by hitting Control-C. Control-C stops the previous program. Let's make this 5 to 1. So this is a Lissajous figure with the 5 to 1 ratio. If we make this 5 to 2, that's what it looks like. Yeah, I'm not really sure what the use is, but they're kind of pretty. That's a Lissajous figure. It's all sines and cosines. Another use of polar coordinates. If I want to specify a point, I can specify it in rectangular coordinates or polar coordinates. If I'm hiking, polar coordinates might be easier, such as if I walk 5 miles at 20 degrees east, so this angle from the x-axis is 20 degrees, and then walk 8 miles at minus 63 degrees east, then 4 miles at 37 degrees east, where do I wind up? Well, I can do that by converting from polar to rectangular. In the xy coordinates, the x's add and the y's add. So I'll do that to calculate this. So I'll first take the points, find the x and y coordinates for the first one, x and y coordinates for the second path, x and y coordinates for the third path, and that's 4 at 37 degrees, 8 at minus 63 degrees. Got to convert from degrees to radians, because MATLAB uses radians. The final position is to add up the x's, add up the y's. So that's where I wind up. There are other ways to do this. This is also where the HP calculator comes in. HPs are, in my opinion, the best calculator ever made. Basically, HP is a company made up of electrical and computer engineers, and not surprisingly, they make really good calculators for electrical and computer engineers. Now, HPs are a little bit different. They've got a learning curve. There is no equals button. The way the HPs operate is they operate on the stack. So when I add x and y, multiply x and y, divide, that's y over x. So before I do an operation, I have to set it up. So if I want to do like 2 plus 3 times 7, I would do 3, enter 7. Well, start out with stack. So here's the stack. If I do 1, enter, that pushes 1 on the stack. 2, enter. 3, enter. 4. I now have a stack of 1, 2, 3, 4. If I roll down, you can see those 4 entries. I can swap x and y. And then when I do an operation like add, that'll add these two together. 4 plus 1 is 5. And the stack pops down. If I now hit multiply, 3 times 5 is 15. 2 divided by 15 is 0.133. There's also a way to do rectangular and polar coordinates. If I do modes, I can do rectangular or polar and complex. In rectangular coordinates, I would input a point like 4, enter 5, complex. There's the x and y coordinate. 8, enter 9, complex. And now we can add the two together. 4 plus 8 is 12, 5 plus 9 is 14. That's one way to do it. There's also polar form. Polar. So I can now say 5, let's do this one. 5, enter 20, complex. There's the first point, 5 at 20 degrees, 8 at minus 63 degrees, 8, enter 63 negative, complex. 8 at minus 63 degrees, add these two together, and it does it. And what MATLAB did, or what the calculator actually did, it probably converted it to rectangular, added them, displayed as polar. All I care about is the answer. Plus 4 at 37 degrees, add. There's this point. It's the 11.91, and the angle is minus 14 degrees. If I want to convert that to rectangular, I just do modes, rectangular. There's the point, x and y. So an application of that. With robotics, oftentimes robotics have rotational joints. There's a motor on the joint, usually with a gear, moving the joint back and forth, rotating it. Suppose I have 3 rotational joints. So I'd call this an RRR robot. I've got 3 joints, 3, and all of them are rotational joints. If the first joint, let's assume this is also a 2-dimensional robot, if the first joint moves this guy, this link, then the second joint moves the second one, third moves the third link, where's the tip? Now standard in robotics is the angle is always relative to the previous joint, and you kind of see that with your arm. If I have my arm at 90 degrees and move my shoulder, if I leave my elbow stiff, the net angle depends upon the angle of the shoulder plus the angle of the elbow. So the total angle for the second link is theta 1 plus theta 2. The total angle for the third link is theta 1 plus theta 2 plus theta 3. That's kind of the standard in robotics. Suppose I want to find the tip position of an RRR robot where the lengths are all 1 meter and it's 2-dimensional like this. Well, I can do that in MATLAB. Let's come up with a function. I'm going to pass the angles, theta 1, theta 2, theta 3. Assume the angles that I pass are in degrees, because they're easier to work with for me. In MATLAB, I've got to convert the angles to radians, specify the link lengths. The origin is at 0, 0. The first link is at cosine theta r1, or L1 cosine theta, L1 sine theta. There's your x and y coordinate. The second link is where the first link is plus its x coordinate and its y coordinate. The x coordinate is L cosine theta, y coordinate is L sine theta. And the angle is the total angle, theta 1 plus theta 2. The third link is wherever the second point is, second link is, plus L cosine theta, L sine theta for x and y. Again, that's the total angle. So once I write that function, I could then plot. Here's where the robot is, the x and y coordinates of each link, drawn as a line, blue line with a dot. And what that looks like is this. So here's the MATLAB function, same thing I just showed you. And MATLAB, I can call it. And functions I cannot run. If I try to run it, I get an error message saying, I don't know what you're doing. Again, it doesn't know what the angles are. I can't call or can't run a function, but I can call it. So if I say, let's do RRR of 0, 0, 0. That's your 0 position, and the tip is at 3, 0. If I say, let's make the first link 30 degrees, that's where it is. Make the second link 20 degrees, third link 50 degrees, there's your robot. Or let's make the first link 130 degrees, second link minus 40 degrees, third link minus 40 degrees, let's make it 50 further, minus 80 degrees, and the third link minus 90 degrees. That's the X and Y position of the robot. And this is left over from last time. I remembered, last lecture, I made it format long. So anyway, I've got a program that'll tell me where the tip position is given the link lengths. That's called forward kinematics. I note the angles, where's the tip? Another problem. Suppose the angles vary with time. What's the robot do? Well, I could try that. So here's the program. Let theta 1 go let's do this. 50 degrees plus or minus 30, the sine wave, theta 2, theta 3. What happens? The first link is 50 plus 30 sine of t. Here's the second link. Here's the third link. I can sit there and do animations show how the robot moves if I specify the angles. If I look at the tip position and plot that for all time, here's what it looks like. I'm not really sure what that shape is, kind of a pretty shape, but that's the result of these angles on that 3-link robot. That's called forward kinematics. Inverse kinematics is actually a lot harder. Forward kinematics is pretty easy. I want to know what is the tip position based upon the angles, and here's the equation. It's the position of the first link plus the second plus the third, add them all up. That's the tip position. Inverse kinematics is go backwards. I know the tip position, what angles put you there? Now this is kind of where algebra fails you. Given x3, y3, solve for theta 1, theta 2, theta 3. That is not easy to solve. But fortunately, there's a program in MATLAB called fminsearch. fminsearch is a really useful program that can solve all sorts of problems, including this one. So start out. What fminsearch does is it finds the minimum of a function. So for example, let's find the square root of 2. That probably doesn't impress you too much. You can do that on your calculator, but let's start somewhere. One way to find the square root of 2 is come up with a function whose minimum is the square root of 2. So to do that, I'm going to pass x, find x squared minus 2. That's the blue line. I want to find the zero crossing. Now square the error that gives you the red line. The minimum is the square root of 2. So again, in MATLAB, what I can do is put this over here. There's my function, root 2. Now in MATLAB, again, I cannot call or cannot execute a function. If I do that, it says, I have no idea what you're doing. What's x? I can call it though. Is the square root of 2 equal to 5? And the answer is not 0. Nope, it's not. Is the square root of 5 4? the answer is getting smaller, that's better, is square root of 5, square root of 2, 3. 2, 1.4. Keep iterating, guess again, until I minimize the answer. Or what I can do is let MATLAB guess for me. And what root2 does, it follows this format, or fmin search. I want to minimize this function. There's my initial guess. And what it's going to do is, as I guess again, I'll display for each guess the guess and the error, minimize E. So when I run this, there's the guess, there's the error, and eventually finds the answer is 1.4142, and there's the sum squared error. Close to 0. If I give it a different guess, say -5, fmin search tends to find the answer close to your initial guess. Now it finds the answer of minus 1.4142. And you can check that answer. If I pass a z, the error is almost 0. 1.4142 is the square root of 2. So that probably didn't impress you too much. So let's try a harder problem. Find the shape of a hanging chain. Now what a hanging chain does is it minimizes the potential energy under the constraint that the length is fixed. You might cover that in some of your math classes. That's actually covered in calculus of variations. Once you complete Calc 1, Calc 2, Calc 3, differential equations, then you can take calculus of variations. Actually, then you need to take signals and systems, then you can take calculus of variations. So it's actually a pretty mean, nasty mathematical problem. But using fmin search and MATLAB, I can find the answer using numerical methods. So the approach is first come up with a function that returns the potential energy of a chain, then have MATLAB optimize it and minimize that potential energy. So here's my function. I'm going to pass the vector z. fmin search just wants a single variable. You can have 9 different entries, but a single variable. So in this case, I'm going to pass the 9 coordinates of the chain y1 through y9. It will then find the potential energy, the sum of y, the total length of the chain. The chain should be 13 meters long, and penalize. If the chain isn't 13 meters, it's 100 times the area squared plus the potential energy. Minimize the potential energy. So here's what that looks like. So if that's the shape of my chain, the potential energy is the cost is 27,000. If I do 7, 6, 5, 4, 3, 3, 3, 4, 5, that's 76, that's better. Maybe a little bit worse. So you can sit there and take your guess. Guess again, or minimize this function. And here's my initial guess. And what MATLAB is doing is it's guessing different numbers for your 9 parameters, figuring out what the cost is, and then trying to figure out what set of variables minimize the cost. Now when I graph it, that really slows it down, but it's kind of fun to watch. Let that run for a bit. If you let that run for a while, eventually it'll kick out and it might find the right answer, or it might kick out due to max iterations. In this case, when I ran it with a random initial condition, it kicked out due to max iterations. To find the minimum, I'm going to take the answer that I got, run it again using that as my initial point. So it tells MATLAB to start where you left off, keep going, can you do better? And eventually it winds up with this solution. Let's see how we're doing. Nope, still iterating. So I can find the shape of a hanging chain using MATLAB. Third problem, let's go back to a robot. Let's find the joint angles to put the robot at position 1, 2. So I'm going to come up with a function in MATLAB. I'll pass theta 1, theta 2, theta 3. It calculates the tip position and then returns the distance to 1, 2 squared. So I want to minimize the sum squared distance to that point. My cost function is going to look like this. I'm going to call it cost, RRR. Here's my tip position, 1, 2. I'll call that previous program RRR of the 3 angles. There's your tip position. The error is the difference in the x's and y's. Return the sum squared error. So it's still running, Control C. Okay. Here's the RRR program that we wrote before. Pass it 3 numbers. And with fn search, it wants just a single variable right here. So the variable is going to be a matrix that has 3 entries. That's my theta 1, theta 2, theta 3. I want the tip to be at 1, 2. So that didn't really do it. Here's the distance to 1, 2, 2 meters. Can I do better? Well, let's increase the first angle to, say, 50 degrees. Better. Let's make the second angle minus 20. And third angle, that was better before. Yeah, not quite. So you can guess again, or let MATLAB guess for you. Call fmin search. Here's my cost function. There's my initial guess. I'm going to sit there, it's going to guess again, and eventually says, okay, I think I found it. And it says, this is the angles that get you there, 44.08 degrees minus 14.41 degrees, 96.3 degrees, and I can check that answer. That puts me at 1, 2. Sure enough. Note that there are multiple solutions to this. If I change my initial condition, let's make it 120. I've got 3 degrees of freedom, 2 constraints, so there's an infinite number of solutions. A second perfectly valid solution is right here. So there's theta 1, theta 2, theta 3. That also puts you at 1, 2. Or a third solution, if I start from here, it'll iterate, find an answer. Here's a third possible solution. That's called inverse kinematics. Given the tip position, find the joint angles. And there are other ways to doing it. If you take 761 robotics, we'll talk about those other methods. but knowing nothing about robotics, I can find the answer using MATLAB and fmin search. So fmin search is just a really useful function. You can solve all sorts of problems with it. If I can set up a function so that the answer that I want is the minimum, fmin search will usually do a pretty good job at finding that minimum. So in summary, trigonometry is all about circles. With sines and cosine functions, you can convert from polar coordinates to rectangular coordinates and vice versa. With sine and cosine functions, you can compute the tip position of a robotic arm. That's called forward kinematics. And with fmin search, I can compute the joint angles that place the tip at a given position. That's called inverse kinematics. And with that, you should be able to solve the homework for week 3. Again, if you get stuck, a good place to go is go to the old homework sets and solutions. So if you go to, check out old homework sets and solutions, and oftentimes there will be solutions to previous semester's homeworks, which are similar, different problems, different numbers, but similar. Kind of give you an idea how to get started. And that's week number 3 for ECE 111.